Okay, hi guys. So in this lecture we'll be talking about some more examples of HEME reaction. Okay, so let's get started. So the first question is here. So in this question you have to calculate how many times HEME reaction takes place in these compounds, the following compounds which I'm going to draw to actually remove the nitrogen from the compounds. Okay, so the question is how many times HEME takes place to remove nitrogen from the given compounds. Okay, so let's see the first compound. We have something like this. So how many times HEME needs to take place? 3 times. Why? In the first time it will be detached from this carbon atom, in the second time it will be detached from this carbon atom, and the third time it will be detached from this carbon atom. Okay, so 3 times HEME needs to takes place here. How many times HEME needs to take place for this compound? 2 times. Why? First time it will need to detach from this carbon atom, thereby forming a double bond here. Second time it needs to be detached from this carbon atom, forming a double bond between this carbon atom and this carbon atom. Okay, let's see the third example. So how many times HEME needs to take place for this compound? So the correct answer here would be again 3. And why is this the case? First time here, for second time here, and third time here. Okay, let's see the fourth compound. Here we have this one. So how many in this case? Again only 1 time. Why? It only needs to get detached from this bond. Okay, let's see uh, um, actually how it happens in this case. I'll just elaborate that we have this compound and we will have what we'll be having CH3I, second Ag2O, and third will be hitting it. So this is HEME reagents. What would happen is CH3 N would attack on CH3, and as a result it would be getting substituted with this one, and as a result it would be getting positive charge, and the negative charge formed after CH3 was attacked by an N's lone pair, it will attack on H plus to convert it into Hi. So we'll get something like CH3 and CH3. Okay, now what will happen again? In obviously we pass CH3 in excess, so again it will combine with CH3 to get something like this one, and I minus, which on reaction with moist Ag2O will form something like precipitation of Agi, and will get something like this compound. This would be attacked by, obviously this is moist Ag2O, so we will have something like AgOH also present. Okay, so this O minus will actually act as a base for and will attack on the on this alpha hydrogen, and we'll get something like this, and from the E2 reaction we will get bond making here and bond breaking here. Finally we'll get something like this. So only one time we need the Ag2 reagents. Okay, now let's talk about some important note. So for E2 reaction to happen, both groups must occupy axial position in case of cyclohexene. Okay, and if any of the group is at equatorial, then no E2 reaction will take place. Okay, so what we have is something like this. Let me first write it down as for E2 reaction, both groups must occupy axial position. I hope you remember axial and equatorial position in case of cyclohexene. Okay, so both groups must occupy axial positions. If one of the groups is at equatorial, then there is no E2 reaction. Okay, so as in this case, if we see that if Cl occupies the equatorial position, this is equatorial position, and we react it with alcoholic KOH in presence of heat, so what will happen is we won't be having any reaction. Okay, but on the other hand, if we have something like this, where H and Cl both are on axial positions, obviously on alternate carbons or adjacent carbons in presence of heat, then we would have the alkene formation via E2 mechanism. Okay, so let us now start with yet another class of elimination reactions called E1cb reactions. Okay, so we have something called E1cb, which is also called elimination 1 from conjugate base. Elimination from conjugate base. Okay, so we have something like this, and we have ETO minus in presence of heat. What will happen is this ETO minus, as expected, will be attacking on this alpha hydrogen or acidic hydrogen rather, and we will get something like minus charge over here and F here. Okay, in the next step what will happen is this negative charge will form a double bond with the neighboring carbon atom, and this fluorine atom would get itself detached from this carbon atom, so we'll get something like this. Okay, so this happens due to the presence of stable carbon atom, and this type of thing is needed. We also saw this thing that when a weak living group is attached, we need intermediate anion character, as we saw in the Hoffman versus Sadzeff video lecture. So in the same case, instead of partial charge, we have a complete carbanion, not carbon character, we have a real carbanion. So this will actually drive the leaving of fluorine atom, which was a, or F minus ion, which was a weak leaving group. Okay, so second point is poor leaving group. Okay, hence this type of reaction takes place. Okay, so let us discuss another example wherein we have something like this. This and okay, so we have something like this. So what happens when we react this with ETO minus in presence of heat? what will be the alpha hydrogen that would be attacked here? Obviously the alpha hydrogen would be, obviously we know that, okay, I forgot a plus sign over here. So obviously we know that this is a weak leaving group, so we'll need a negative charge on this carbon atom. And why this is more acidic alpha hydrogen? Because if we get a delta negative here, this is obvious. If we get a delta negative here, or a negative carbon ion here, will get, or a negative charge here, it will be getting involved with the resonance with a highly minus M effect. Hence it would have a stable carbon ion. And second point, it is having a poor leaving group. Hence both the conditions for E1cb are met in this case, and hence ETO minus will actually react on or attack on this oxygen hydrogen atom. So what will be getting as a result? We'll be getting something like, obviously this will be having, this was regarding the stability, but it would be having a good minus character, so will form a bond between itself, and this nitrogen atom will take away its electron. So what we'll be getting is something like, this would be our final product. Okay, let's see another example. Suppose we have something like this, and we have F here. This is a weak leaving group, and negative charge here would be stable. Hence both the conditions for E1cb reactions are met, and if we react it with ETO minus in presence of heat, it would be attacking on this alpha hydrogen. So we'll be getting something like, and CH3. Okay, so this would be the product formed. Okay, so with this we come to an end of this lecture. In the next lecture we'll be discussing upon conditions which are required for E1cb reactions, and then we'll be having a comparison between substitution and elimination reactions. Till then, good luck and goodbye.